Good morning or good afternoon, everyone. So we are going to go forward with the second talk by María Esteban on the topic of functional inequalities and improvements. María?
Thank you, Ludmila. Thank you very much. So I will continue with what I was explaining on Monday about functional inequalities and improvements. And so I recall very briefly what I did last time. So last time I spoke a little bit about symmetry and symmetry breaking issues for PDEs and variational problems. I discussed in an abstract way and then in a concrete way some functional inequalities, in particular Gallardo-Nirenberg Sobolev inequalities on unit spheres. And I explained why functional inequalities play a very important role in various fields of mathematics like PDEs, analysis, differential geometry, probability, and mathematical physics. So when I explained one of the proofs available for the Gallardo-Nirenberg Sobolev inequalities on spheres, I explained how one can use linear and nonlinear flows to prove them, flows meaning evolution problems, and seeing how some quantities evolve along those flows. At the end of my talk, I said something about improved inequalities and stability. And also during the talk, I spoke about the application to spectral estimates for Schrödinger operators, which is one of the main reasons why in quantum mechanics, mathematical physics, people are interested about functional inequalities. So today I will continue. What I will do is to look at other inequalities, which are a little bit different. And I will explain, without going into many details, that we would have, studying those inequalities, successes for some of them, and have successes or failures for others. So I will also try to explain why, in some cases, we are able to prove optimal results and why in others we are not able to do that. So I will speak about finding the best constants in the inequality, analyzing the qualitative symmetry properties of the extremal functions, and discussing a little bit about stability. And at the end, I will say something, and along my talk, I will speak about open questions and new directions of research. Okay, so the first one I want to address today is inequality for which I have been working for many years, which looks not too difficult, but it looks like the inequalities I wrote last time. You have some gradient squaring, some integral, and then you are controlling some LP norm square. The problem is that here you have weights in the inequality, so you have that there is some dependence on the space variable, and these weights can create singularities or they can create degeneracy for the corresponding equations, depending on the signs of the exponents of these weights, for example. So these inequalities that are called Caffarelli-Kohn-Nirenberg inequalities were introduced by these three mathematicians in 1984 when they were discussing about the possibility of having singularities for the Navier-Stokes equation. So you see, in a very different topic, in fluid mechanics, and they saw that in order to analyze the possible appearance of singularities for the Navier-Stokes equations, a very interesting tool would be to understand these inequalities. Okay, so they introduced them in those papers, and they proved in an auxiliary paper that these inequalities hold true whenever you have that the parameters B and A satisfy this condition. B is between A and A plus 1, A and B, and the parameters that are in the exponents of the weights here. And well, this is dimension 3, in dimension 2, something different. A has to be different from dimension minus 2 divided by 2. And also they show that there is a necessity of having a relation between the exponent P, which appears in the LP norm, and A and B. So they prove that these inequalities hold true under these conditions. But they didn't go into details of what is the value of the best constant, how are the extremal functions, etc., etc. Okay, so Let me just make a little remark. So we have that B, the parameter B has to be between A and A plus 1. So if we take in this relation that defines P, we take B towards A to the lower end of the interval, you see that if P minus A goes to 0, P by this formula goes to the Sobolev, the critical Sobolev exponent that I talked about last time several times. And the inequalities actually converge towards Sobolev inequality. Instead, if you take B going to the upper side of the interval, it goes towards A plus 1, then P by this formula goes to 2. So in some sense, what this says is that these inequalities, which look a little bit strange that they introduced, are interpolation inequalities between Hardy and Sobolev inequalities, which are very well known. Now, let me make a last remark in this slide, is that as I pointed out several times on Monday, when you have such an inequality and when you have the best constant, you call it CAB, then 1 over CAB is the minimum of a functional, which is defined like this. Okay, so that I spoke about that several times on Monday. So this minimization problem is totally equivalent to this inequality. And so sometimes I will speak about extremal functions for this inequality, meaning functions for which you have equality here. And it will be the same as speaking of minimizers for this minimization problem. Okay. Now, of course, this inequality, you look carefully, you see that it's invariant under rotation because RD is invariant under rotation. The weights are modulus of x to some power invariant under rotation, the gradient operator also. So these inequalities are invariant under rotation. So you could expect that the solutions, the extremal functions, the best solutions, the global minimizers of this variational problem would also be radially symmetric. But as we saw last time, there are cases in which this hope is true and sometimes it is not true. So we don't know a priori whether the global minimizers of this problem will be radially symmetric or not. Of course, if they are radially symmetric, then it will be very easy. We will be in dimension 1. The functions will depend only on the modulus of x on R, and so it will be easier to compute the value of the best constant. So it's important to know whether the minimizers of this problem or the extremal functions of the inequality are radially symmetric or not. It's really important in applications, for example. Now, there very quickly, I will put some names here. It's not difficult, not difficult, it took some effort at the time, to prove that in this green zone, so here I am drawing the strip B between A and A plus 1, okay? So the strip in which the inequality takes place, this A is t minus 2 divided by 2, that is to be avoided. And to the right, I don't talk about it because you can transform the left to the right by some transformation. Okay, so let's look at this half strip. So in this green zone, you can prove that the minimizers of the problem or the extremal functions exist and they are radially symmetric. And this has been proved by a lot of people in different moments of. So the first proofs were by Aubin and Talenti. Aubin was a geometer, differential geometer, Talenti an analyst, and what they prove is that for the particular case A equal to B equal to 0, which is this point here, this is Sobolev inequality, they proved that the extremal function was radially symmetric, and they gave the exact form of the equation. So that was in the 70s. Later in the 80s, there's a work of Elliott Lieb in mathematical physics. He was interested in these inequalities in the particular case when A is equal to 0, some application in physics, A equal to 0, B between 0 and 1. So this segment here. And for that segment, he proved the existence of solutions and the radial symmetry. Okay, and then there were other people working in the other sets. So there's been a lot of people proving in the end that in the green zone, the solutions exist, the minimizers exist, the global minimizers or the extremal functions, and they are radially symmetric. And it took effort. I mean, it took maybe 20 years to describe all this. But then in 2001, Katrina and Wan proved a surprising result, a striking result. They proved that in this half-strip, global minimizer extremal functions always exist, but that there was a zone, this red zone, in which when you look at the minimizer among radial functions that is known explicitly, this minimizer among radial functions, if you look at it in the total space of functions, it is unstable. You look at the Hessian or the functional around that point, and you see that in the red region, that Hessian has negative eigenvalues, which means that these guys, which were minimizers among radial functions, can't be global minimizers because they are saddle points. They are not local minimizers, so they are not local minimizers, they can't be global minimizers. And they identified practically the zone. The zone was not completely well described, so the work was totally completed by Felli-Schneider in 2003, 2 years later. So these four mathematicians have completely identified the zone of the for the parameters in which the radial minimizer, the guy who minimizes the energy among radial functions, is not a local minimum in the whole functional space. It's not stable. So remained the doubt about the gray zone. What happens when you are not in the red zone, I mean, in this area, and you are, you are the local minima, the radial minimizer is local minimizer, so it could be global minimizer. I mean, there is no instability, it's stable, but is it the global minimizer or not? And there's been a lot of people trying to do that for some years, maybe 10, 15 years. And there was a conjecture that we could have this drawing with the green like that. So what this conjecture says is that the only possible source of symmetry breaking is the instability of the radial minimizer. So whenever the radial minimizer is a local minimum, it will be a global minimum. And that our group, but other groups were working on that for a number of years. And finally, we solved the conjecture. We wrote several papers, partial results. And in 2016, with Dolbeau and Loos, we proved the conjecture. We proved that in the stability region, if D, the dimension, is larger than or equal to 2, the optimality indeed is achieved by radial functions. And this theorem is really not an easy result. I mean, it took a lot of efforts to have the idea of the proof. And when we had the idea of the proof, still, it was technically very, very involved. I will not go into details of the proof, but I will explain a little bit. So the idea of the proof is to base ourselves in this idea that I explained last Monday of Bakri and Méry, of these probabilists, that they introduced this Carré-Duchamp method, these flows that you have some energies and you look at the decay properties of these functionals. And then we tried to use that idea because we thought it was a very robust method that would help us. We tried a lot of flows, different possibilities for some years. And in the end, what we managed to do was the following thing. We did some changes of variables and functions. I will not write them here. And we managed to write the inequality in another manner. So we managed to write the inequality like this. We have the integral of u with respect to some measure. This measure is in polar coordinates. You see R and the angles. So in polar coordinates, this is the Lebesgue measure in dimension n, but it's strange because we are integrating in dimension d, and this n and this d are not the same. So we write the inequalities, we transform the inequalities, Caffarelli-Kohn-Nirenberg inequalities into this inequality with this integral less than a constant times I, and I this time is another integral with some kind of gradient. It's not a gradient, I mean, it's a complicated expression, but the nice thing about writing things like this is that we have the same weights, the same measure in the two integrals. So we have again here the Lebesgue measure in dimension n. Okay, so once we had this idea that came by luck, I will tell you practically by luck. Once we had this inequality, we thought that we could use really the idea of Bakri and Méry, this idea of using linear, nonlinear flows to treat this problem. Okay, so what was the strategy? we had to find a flow, a nonlinear evolution problem, for which when alpha is less than alpha fs, and this is just, I'm not going into details, alpha is a parameter that appears in this differential operator. And this alpha fs, this condition corresponds to the green zone, to the zone where the radial minimizer is stable, is a local minimum. Okay, so what we had to prove is that in this zone, when we have a stability of the radial minimizer, along the flow that we are going to find, the integral of u will be constant, and this integral of this functional I will be decaying. You see, it's again the same idea I talked about last time. We need to prove, to find a flow for which the functionals in which we are interested are Lyapunov functionals. That's the idea. Okay, so what did we do? After some years of work and some trials of different flows, we found a very simple flow you could think of. It's a parabolic equation, nonlinear. M is 1 minus 1 minus n, so it's less than 1. This is a parabolic equation because L alpha is elliptic operator that is written here in polar coordinates. And you can see that in polar coordinates, this operator is practically like the Laplacian, but we have a constant alpha square in front of the radial derivatives. So it corresponds to a stretching of the space of the variables in the radial direction, not touching the angular direction. Okay, so we consider this a flow for reasons that I don't have time to explain. After trying other flows, I can tell you this was not the first one we tried. And by performing lots of calculations, by using a lot of differential geometry tools we needed in the proof, in particular, for example, the very well-known Bochner-Elixnerovich-Weitzenbach identity, which relates the Hessian to curvature, Ricci curvature, and things like that. And finally, by proving quite delicate regularity results at the origin and at infinity, we could prove the conjecture. And I stress this last item because the regularity results you see in Caffarelli-Kohn-Nirenberg inequalities, we have weights, and these weights can create, as I said before, degeneracies or singularities at infinity or at the origin. And so the solutions of the equations can have bad behavior near the origin or at infinity. And so we needed regularity results for the solutions, and that was the toughest part of the proof. Okay, so this is really not an easy proof. So the idea is the same idea of Bacri-Emery, to use this flow and prove that we had some decay for the functional I in along this flow. So we did that, but to be honest with you, that proof was formal. It was not rigorous. Why? Everything worked very fine, but we couldn't really say that that was a proof as mathematicians. Why? Because we were unable to prove that this parabolic equation that we were using had solutions for every t. We didn't know of any result. We talked to a specialist in nonlinear heat equations, and they didn't know. They were not able to prove, and I think up to now, in general, it's not known whether this parabolic equation can be solved for every t. So our proof was formal in the sense that we were supposing that we had solutions of the parabolic equation. So it was a little bit frustrating, but we found a way to solve the problem. We had an idea of doing an elliptic proof. So what we did, maybe I will not go into details here, what we did was an elliptic proof. What we did was to use the flow, yes, all the computations we had done that were formal, not rigorous, we used them only, we needed them only at time t equal to 0. So we differentiated everything only at time t equal to 0, and we were able to prove the conjecture in this way. So at the beginning, we had our proof finished, we were happy, but then we were trying to find some results. We talked to a specialist in nonlinear parabolic equations, and nobody was able to give us the proof of the existence of solutions for the parabolic problem. So we had to think about changing our strategy and looking at the problem in a different way. So we noticed that we had to differentiate and use the equation only at time t equal to 0, which actually is an elliptic proof, and we don't need the flow for all times. Okay, so I will not, I have a slide here. I think it's maybe too technical for a general audience. Okay, so we did that. So the thing I wanted to say is that the proof is really very involved. It's a difficult proof. It's a long and difficult proof from the mathematical point of view. But what I wanted to say is that, in my opinion, what was interesting about this result, it was, how to say, a proof of the fact that this strategy of Carré-Duchamp method of Bacri-Emery is really very, very powerful. It can really be used for many, many different situations, and the strategy is always the same. Of course, when I have presented these works in front of an audience that is specialist, they say, yeah, but how do you found this flow? And that's the problem, is that you are given an inequality, and there is no recipe for the flow that is well adapted for the inequality. So of course, the people, when you work in this for some years, you know, you have how some recipes, you have some ideas of possible flows, etc., etc. You have some experience, but there is no clear recipe to find the good flow for the good for the inequality you are studying at the moment. Okay, so it was a little bit lucky that we managed to do this, but in any case, for me, it shows the strength of this Carré-Duchamp method that Bacri and Emery found. Okay. So now that I spoke about this, let me just very quickly say that these inequalities, as I said, they were interesting, for example, in differential geometry. Why people are interested in these inequalities? I'm just giving you an example and giving you a corollary of the theorem that I have just discussed in global analysis, if you want, as is called nowadays, PDEs on manifolds, okay? So you, for example, take in the Caffarelli-Kohn-Nirenberg inequality, you make a change of variables that is well known in PDE community, which is called the Enden-Foley transformation, which is this one. Don't look at the details. There is a transformation that transforms the whole RD into the variables S omega. S is minor log of R, and omega is just omega, the angle. So this transforms the space RD into a cylinder that is R cross SD minus 1. So you transform RD into an infinite cylinder, okay? Or an infinite, the boundary of the cylinder, okay? So by doing this transformation, is very nice. You see that the Caffarelli-Kohn-Nirenberg inequalities transform very easily, actually, into an inequality of the same kind in the cylinder, but with no weights, which is quite comfortable, because the weights are really a complication when you are analyzing solutions, differentiating, etc., etc. You need a lot of regularity. Here, the regularity issues are not there. So you can show that the two inequalities are equivalent. And we have actually played with that. In the proof, sometimes we use this, and sometimes we use that. I mean, because it really helps to not to have weights. Okay, so we have this very easy inequality now in the cylinder, in an infinite cylinder. Okay, and then I explained the other day that associated to any inequality, you have an Euler-Lagrange equation that now, for the cylinder, is a very easy, very simple semilinear problem. You see, it's just minor Laplacian phi plus mu phi equal to the p minus 1 power of phi on the cylinder. An easy, I mean, to write equation, but not so easy to study. It's a nonlinear problem on an infinite manifold. It's not so easy to analyze. Well, as a corollary of the previous theorem, the theorem we proved for Caffarelli-Kohn-Nirenberg inequalities, we can, as corollaries, first, we can discuss for which values of mu, the parameter which is here, the positive solution of this equation, nonlinear equation on the infinite cylinder, depend only on the variable S and not on the angles that corresponds to radial symmetry in RT. And we can also get uniqueness result for the positive solutions. So this is really an important result, and unique is not easy to find uniqueness results for nonlinear equations. And so this is just a simple corollary of the study we did for Caffarelli-Kohn-Nirenberg inequalities. So that wasn't bad, just for free. Also, we can find optimal estimates for the first eigenvalue of a Schrödinger equations on this manifold or the infinite cylinder. I mean, there are not many available results in infinite in non-compact manifolds. And then we can also, but this is not a corollary, we can also prove this kind of results for compact manifolds. For compact manifolds, we need to adapt all these methods. It's not exactly the same method we use, but just if you wanted to tell, and do you have results for compact manifolds for manifolds which are not exactly spheres and things like that? The answer is yes, but I am not have time to speak about it in this talk. I chose not to speak about that. Okay, so you see that all this business of inequalities, we see the link with probability, we see the link with differential geometry, we saw the link with mathematical physics. And now that I have spoken about it, let me just speak in the remaining 20 minutes. Let me go slowly about other inequalities you could study or we have studied in which things are not so clear and so easy. So up to now, I have given to you the positive story, the successes, the optimal results, the conjectures proved, okay? Now I'm going to talk to you about problems in which sometimes we are able to give optimal results. Very often we are not able to do that. And I will try to explain why. And so I will list open problems in this area. Okay, so the first area, the first extension I will speak about is the case of magnetic problems. Magnetic problems, for example, in mathematical physics, correspond to looking at Schrödinger equations when you are looking at electrons or systems, molecules, atoms, etc., I mean matter, which is affected by the presence of an external magnetic field that happens very often in real problems. And so how you take that into account from the mathematical point of view, you are not a physicist. Well, what you have to do is to replace the gradient operator by the magnetic gradient, which is just the gradient translated by I times A, where A is which is called the magnetic potential, and it is linked to the magnetic field by the relation B equal to curl of A. Okay? So for a given magnetic field that is acting on whatever matter you are looking at, you look for a magnetic potential that satisfies this relation. It's not unique. There are an infinity of possible A's, but that doesn't matter. It doesn't create many problems. And then what you do is to change in your equations the gradient, normal gradient by the magnetic gradient. This is just a covariant derivative, if we are speaking in terms of geometry. Okay, so you do that, and you do that, for example, it's just an example. I could give many other examples. You are interested in looking at inequalities as the ones we were talking about earlier today and last week. So you have inequalities for functions in some space, and you want to see that the LP norm of the functions in this space are bounded above by the L2 norm square of the functions plus the L2 norm of the gradients. But now we replace the usual gradient by the magnetic gradient, okay? So this is, and you do that for P's as last week, between 2 and 2 star, which is this Sobolev exponent. Okay, so as I explained last Monday, you are interested in understanding what is the value of the best constant and how it depends on the parameter alpha that is there. Okay, this is a possible question. It's not the only one you can ask yourself, but this is just an example, okay? So this is something we discussed the other day in the case without magnetic field, in the case without when you have gradient of psi. So is it so different when you introduce this magnetic field, when you modify the gradient? And the answer is yes. What we managed to do without magnetic field now sometimes is very difficult to be done. And I will speak about two examples. One is the example of constant magnetic fields. So you have a magnetic field which is a vector, which, for example, you point in the dimension 3, you point it in the z direction, for example, 0, 0, b. B is a constant, okay? Positive or negative is not important. So you have a constant magnetic field. It doesn't depend on which point of the space you are. The molecule or or the atom you are looking at just sees a constant magnetic field around it, okay? And then you can see without very easily that an associated magnetic potential can be, for instance, is one of them, B divided by 2 minus x2 x1 0. You can make the computation and see that the curl of A is equal to B. Okay. This is a very important case in quantum mechanics, okay? Constant magnetic fields are all over the place when you look at atomic or molecular systems. And what I can tell you is that I'm not going to state any theorem or anything, is that we have looked at this kind of inequalities for constant magnetic fields in dimension 2 and 3. And I did that, I didn't put the names, I should have put the names. I have done that with Dolbeau Loss and Ari Laptev, also from London. And we have had very few successes. So we have some partial results to say something about the value of the best constant. When you have a constant magnetic field, we have some conjectures, we have some partial results, but nothing optimal. And we have conjectures in dimension 2, even no conjecture in dimension 3 about what is the value of this constant. So really very difficult problem from our point of view. We really were not able to do that. So why we were not able to do that? Well, because we were not able to find a method to study this problem. And in part, we tried again to use flows, of course. This is what now a tool that we like and we use very easily with other inequalities. And we have been unable to find a flow in the sense of what I described, an evolution problem that is well adapted for this problem. So we have been unable. So maybe one day we will be able, or somebody else will do it. Or maybe at some point we will be able to find another proof, another method of proof. For the moment, the problem is quite open, okay? Easy inequality, easy magnetic field. Practically, the question is open. We have very partial results. Now, there is another case, which is called the Aharonov-Bohm magnetic field, which is also important in quantum mechanics. And this is a case which is opposite, I would say, is in the opposite side of magnetic fields with respect to constant magnetic field. Why? Because this is a magnetic field which is quite singular. It's a constant times the Dirac mass at the origin, or at some point. Okay, so you see it's very, very singular. It's not bounded like the constant magnetic field. And the support is just 1 point. So you see it's really very different from the constant case. So in the case of this Aharonov-Bohm magnetic field, Aharonov-Bohm are physicists who introduced this because they wanted to study some physical problems. I didn't go into the explanation here. You can see that you can consider associated magnetic potential this guy, A of x, which looks a little bit like the previous one, only you have singularities. You know, you see x2, x squared minus x1, x squared. Well, the singularities are normal because you have a very singular magnetic field. So this Aharonov-Bohm magnetic field, which is also interesting in physical applications, is more favorable for our studies, for the functional inequalities we study. I will not go into the details, but what happens is that we are not able to find an associated flow, an associated parabolic problem, which is good for this problem, but we are able to make some comparisons, etc., and indirectly use some flows. And so in this case, you can look in my list of publications, you will see if you are interested, or you ask me, and I will send you references. So in the case of Aharonov-Bohm magnetic field, we are able to prove a lot of results, not optimal in most cases, but quite good. We have to close the subject, but it's almost closed, okay? So we have a bunch of good results in this case, and not in the constant magnetic field. Very different situation from the mathematical point of view, okay? So this is an area in which there are still a bunch of open problems. Okay, so why, let me say why we think that this is a difficult problem. Well, this is a difficult problem because the Euler-Lagrange equations are not scalar equations. in my previous talk and in the first part of my talk today for Caffarelli-Kohn-Nirenberg inequality, you can see that the associated PDEs are scalar equations. Okay. Here, when we have magnetic fields, the waves associated to the problem, the optimal waves, will have non-trivial phase, they will be complex valued, and they will have non-complex, non-trivial phase and modulus. So the Euler-Lagrange equations are systems of equations, systems of two equations, one for the modulus, one for the phase, and they are coupled. So what you find here, we are forced to consider systems of two coupled nonlinear equations. And we know, I mean, as PDEists, we know that studying systems is always far more complicated than studying PDEs, scalar equations. So of course you will tell me this is maybe technical. Well, maybe, but we don't know. In the end, what we think is that we don't understand how to adapt the methods that exist for scalar equations, the flow methods, the Carré-Duchamp method of Bacri-Emery, all those methods that exist and very nice for a scalar case. We don't know how to adapt them to this case, to the case of systems. And maybe we have to adapt them, or maybe we have to think of another strategy of proof. But for the moment, we are really in the middle of lots of open problems. So this is extension 2. We really think that studying inequalities involving value functions and vector value functions, and systems is very important. Why it's very important? It's not only the magnetic case, it's also that, so I was explaining here in the first paragraph what I already said, this fact that the Euler-Lagrange equations are systems. And it's not the only case, the magnetic case. There are many cases in physics, especially in quantum mechanics, in which you are interested in studying wave functions that are vector valued. For example, if you look at molecules, atoms, etc., if you think about the spin, if the particles, you consider them with a spin, then you will have functions which have values in C2. Okay, so there are many, many problems in quantum mechanics, in other areas of physics, in which you have the wave functions have vector valued. So the corresponding Euler-Lagrange equation will be systems. And this area is practically open. This is totally, we don't know. I mean, this is interesting in physics, and we don't know how to deal with inequalities in this area. This is a totally virgin area, I would say. Very, 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 very few results. Okay, so this is one of the directions in which we would like to work in our group. But I think that there is room for many people. They are interested in inequalities and no methods at all. So there's a need of many people having imagination and finding new methods of proof. Another extension is what I finished with last time, and I just was very short. I'm going to speak a little bit more about it. It's an area in which there is a lot of activity nowadays, and it's the question of improving inequalities, and in particular the stability question, which is related to the following question: how well can one measure the distance to the optimizers of an inequality by the inequality itself? And in particular, can one prove that if the function almost attains equality, so you are almost, you look at the inequality and it's almost zero, but not zero, the difference of the two terms, can you prove that then these functions will be close to one of the minimizers? And this is not an easy question. I said something about it last week. The question, I rephrased it already the other day, is you have this inequality, f larger than a constant times e in some functional space. So you know that f minus ce is a function which is non-negative, but you want to see if you have more than that. Can you say that for non-optimizers, you can improve this information? You know that it's non-negative, but maybe you can measure how non-negative it is. Okay, and in particular, you are interested in measuring the distance of u to the minimizes to the extremal function. If you have extremal function for the inequality, you will have equality here. So f minus c will be equal to 0. So you need in the right-hand side something that is 0 when you have an optimizer, okay? That's why we think about the distance to the set of optimizers. So these kind of inequalities are called stability inequalities for that one, okay? There are many people working in this area. I said that the other day without going into details. And the other day, for example, I already stated something very quickly at the end of my talk. I told you, for example, in the case of the Gagliardo-Nirenberg inequalities on the spheres that I presented last time, you could rephrase them. I rephrased them actually. I rewrote them last time on Monday as the difference of I minus dE when I defined what I and E were. Okay, so it was written like this, these inequalities. And I told you very quickly at the end of my talk that the proof of these inequalities relied on looking for a nonlinear equation or a linear equation and showing that along this nonlinear equation, the quantity that we want to show to be non-negative, I minus d, is decaying, okay? So the proof was relying on proving that this quantity, I minus d, is decaying, okay? But as I told you, we could go further. We can see, we can see how negative this guy is, okay? And by doing that, by studying that in detail using some differential inequalities, I stated that quickly last weekend, for example, we're able to prove that I minus dE is actually bound below by something which is a complicated expression, but is explicit expression, where here you see the difference of any function u to some power minus its average on the sphere, okay, which is a constant. Okay, so you see that this goes in the direction of the stability I was trying to introduce now. The fact that when you have an inequality, you can try to see how positive this is when you have functions that are far from the optimizers. If you have far from the optimizers, you have here this norm, how positive you can have here, okay? Now, this question is quite trendy nowadays in the PDE, in the variational theory, in a large community in analysis actually. And I'm going to give you some examples, quick examples. For example, for the Sobolev inequality, there is this very famous Bianchi-Eknel inequality that says that when you take the two sides of the Sobolev inequality and you take the difference of the two of them, you know that this guy is non-negative, but it was proved by Bianchi-Eknel that there exists a constant such that this difference that you know to be non-negative is bounded below by a constant times the infimum over all functions h which are optimizers for the inequality of distance in the terms of L2 norm to the square of the difference of the gradients. Okay, so Bianchi-Eknel could quantify how positive this thing is if you are far from the manifold of the extremal functions. Okay. Now, this was a striking result. Many people, I mean, this paper is really very, very highly quoted. The problem of this proof is that this was done by a compactness argument and that they had no idea what the value of this constant is. It's a positive. They proved that there exists positive constant for which you have this, but no idea whether k is very small or not. They have an upper estimate, but not lower estimate. Okay. So this result triggered a lot of activity in the PD community and analysis in general. And there have been other results for other inequalities. For example, for the famous Hardy-Middlewood-Sobolev inequality, there is a result of Carlen, recent one, who proves the same thing, same kind of result, again with a constant that is not known. For Gagliardo-Nirenberg-Sobolev inequalities, Dolbeau, Toscani, there are many people have been working on this, and you have also this kind of results, again, without knowing the optimal value of the constant. So there has been a lot of activity, no time to speak about it, but just to tell you that this is a very trendy and active area nowadays. Just a little remark. to tell you that you see always in my inequalities here, you see always that the remainder term is always quadratic, okay? And this was proved actually by Rupert Frank. Rupert Frank proved that in all these inequalities, quadratic is the least you can have. You cannot have subquadratic. But in some cases, and there are two examples that I know in the literature, one given by Rupert Frank himself and one given by Alessio Figali, they gave particular examples in which the remainder, the error term, was quartic. Okay, so in some degenerate cases, you can go above quadratic, but never below. Yes, this is just a remark. Now, very quickly, let me say that in recent years, this area, there are many people working in this area, not only for Sobolev inequalities and this kind, but also in when you look, for example, in complex analysis, because you can also deal with the isoperimetric inequality, the Brand-Minkowski inequality, etc., etc. So there are people also in complex analysis that are interested in seeing if the inequalities they are used to can be improved in the sense I described before. Okay, so many people are working in this. I put names here, but well, no time to go into the details. Many people in Italy, but not only. Some people in the US, some people in Germany. I mean, there are many. I mean, I put a long list of people who are working on the stability for analytical and geometric inequalities. But as I said, in most of these results, nothing is known about the best constants in the remainder term, except there is a result interesting by Figali, Maggi, and Pratelli, where they use mass transportation and rearrangements to, in a particular case, which is one Sobolev very particular inequality, in which they are able to estimate the best constant. Many people are looking for that at the moment. It's really a very hot subject. And also there is a very recent result, this is last year, by Bonforte, Dolbon, Nazaret, and Simonov, where they study Gagliardo-Nirenberg inequalities and Sobolev inequality, and with additional restrictions by entropy methods. I mean, it's a partial result, but it's the first constructive result of proof by stability for to have really the exact value of the best constant. So they have a lot of additional restrictions and hypotheses and all that. It's a 180 pages paper, quite difficult, but it's the first real result of this kind. Okay, so I would like to quote it, even if it's a little result in some sense, but it's the first one, so it's important. And so let me just finish now with my last slide about open problems. Some of them I already spoke about. So I think that in this area, the new directions, the open problems, if people are interested to work in this area, first is inequalities for systems and inequalities for vector valued functions. That is interesting for applications, quantum mechanics, quantum chromodynamics, other areas of physics. So for applications looking at inequalities in vector spaces with vector valued functions is practically totally open area and very important for applications. Magnetic inequalities, I already spoke, is part of this subject in some sense. And as I said before, almost everything is open for constant magnetic fields, and some open problems also for Aharonov-Bohm and other magnetic fields. Okay, so in this area, something has been done, in particular by my group, but not only. There are other people who have worked in this area. For systems, practically nothing is known. And the last topic that is really, as I told you before, very hot, is to find constructive estimates of the best constant for stability estimates, for improved inequalities, okay? So this is, as I tell you, very, very hot area nowadays, but the real problem is not solved. So, for example, proving that the best constant in the Bianchi-Ekner inequality is estimated from below by something, which is explicit. I mean, to prove that, I think would be a very, very important result. So with this, I will stop. It's just time for me to stop. Thank you very much.
Thank you very much, Maria. Any questions? Lev?
I just wanted to thank Maria for very interesting talks. I enjoyed tremendously both talks. So I want to applaud Maria for wonderful, wonderful talks.
Thank you very much.
I will join Lev as well. These are fantastic talks. Thank you, Maria. It was such a pleasure to hear and then just to understand what's going on. Thank you.
Yeah, I tried to do something not very technical so that people in different areas could follow it, but of course it's frustrating because I couldn't speak about the proofs. Well, anyway, that's life.
Maybe continuing on the vector valued inequalities. So it's also for various systems, like let's say of Schrödinger type equations or something like this, right? Where you have the system and you want to obtain, but more of the, is it that type you considering? Maybe you can just elaborate a little bit more on the vector value.
Not necessarily. I mean, you have many of these inequalities or variation problems, minimization problems, and the functions are vector valued. And the problem is that what do you use to prove symmetry in general? This flows is a method that has come later. Normally, people have used for a very long time to prove symmetry of solutions of PDEs rearrangements. Or moving planes is a very, very famous method in PDEs, moving planes. And none of these works for systems, you see. So, for example, there is a famous problem which is called the Schirmer problem in chromodynamics. And it's a problem defined on the sphere, and you want to prove that the solutions are pointing, the vector is pointing in the radial direction outside of the sphere. This is a very famous, the Schirmer problem in physics. Physicists have done a lot of simulations. Everything about the conjecture is that you have symmetry. For the minimizer, it's a topological problem with some degree involved in it. It's very interesting from the mathematical point of view. I worked on that when I was young. And actually, there are several proofs of symmetry in the literature, but they are all false. Okay, they were proved lately. There was a mistake. There are 3 or 4 proofs in the literature. So it's a very interesting problem in physics. And you have these vector functions, and you don't know what to do with them. You don't know how to rearrange them. You don't know how to find a flow. No idea how to do, what to do. No idea.
And related to this, have you looked at, because there was a paper of Brenier on some kind of symmetrization for vector valued functions, but I don't remember exactly. I think I tried it for Skirm and it didn't work. So unfortunately.
Yeah. No, we haven't tried, but this is a good idea. Maybe in the problems we are looking here with magnetic inequalities, we could. Yeah, no, we didn't. We should have actually, but we didn't.
Anyone else? Well, if not, let's thank Maria again. And we really hope to see you in IMSA in near future, in person. So.
Okay. Yeah, it could be a pleasure.
You are a Spanish speaker, so.
Yeah, I can.
You'll be at home in Miami. Yeah, that's right. You'll be indistinguishable.
Yeah, but it's not easy to speak in Spanish math. I'm not used to speak math in Spanish.
No, English or Russian or French will be sufficient.
Yeah.
It's outside of the universities, right? But that's where Spanish is very useful.
I was in California in the last month, and I was speaking a lot in the streets. Okay, thank you very much for the invitation. It was a pleasure.
Thank you.
Thanks.
Okay.
Bye-bye.
Bye.